Hi, in this chapter we are going to talk about correlation and dependencies. We will start with the Pearson correlation and show the relationship to the R-squared measure and introduce a more general term of feature dependence with the mutual information as an example measure. Let's start with the correlation, the Pearson correlation. When we read about the correlation, oftentimes the Pearson correlation is meant. It should be noted that the Pearson correlation is only able to measure linear relationships. And it has also a nice geometric interpretation that we will look at here at first. Let's focus on the numerator here. The numerator is a sum of two values that are multiplied. Basically, what we are referring to here is the multiplication of this and this part. And because here is x1 of observation 1, for example, if this instance here is the first observation, we are taking the distance here, and for this distance here, we are looking at the second feature and take the difference of the second observed feature value with the mean value of, here in that case, it's the number of bike rentals. These distances or these two values here are multiplied in this numerator here. Essentially, multiplication of two values from a geometric perspective is nothing else than the area of rectangles. Here in that example, we are measuring this length here with this distance, and this length here, multiplying these two lengths results in the area of this rectangle over here. So basically what this numerator here tells us is that we are summing up over rectangles, and these areas can be either positive or negative. So they enter the sum with a positive or negative sign, depending on the position of the data points. For example, if we are over here in this region or in this region, we will always have a positive sign. If we are here or here, we will always have a negative sign. The reason is because the mean value here is always smaller than the observed value from observations that lie above this line and on the right hand side from this line, meaning that the two values that are multiplied for points that lie in this region here are always positive. Here, the two values will be always both negative, and the product of two negative values will be positive as well, meaning that from here and here, we will always have two positive areas that go into this summation here. For points that are here and here, we will always have negative areas. And if the sum of the positive areas dominate the negative areas, we speak of a positive correlation, meaning that if we have much more points in this quadrant here, and we can already visually see what this will look like, and this speaks for a linear relationship, because we can think of a line that is in here that tells us there's a positive trend. While if we have negative areas that dominate the positive areas, we would have much more points here, and summing them up will dominate the sum of the positive areas, which will lead to negative correlation. Of course, if both areas, positive and negative, cancel out each other, we will have a correlation value of 0, meaning that these two random variables are not linearly correlated. Let's look at another measure of linear dependency, which is the so-called R-squared measure. The idea here is simple. We are just fitting a linear model between the two random variables that we are interested in. Here in this example, it's temperature measured in Fahrenheit and the number of bike rentals, for which we want to estimate a linear dependency. And we try to fit a linear regression model and look at the slope. If the slope, for example, would be 0, this would just be a horizontal line meaning that we wouldn't have a linear relationship between temperature and number of bicrantals. Now, of course, in this example, we don't have slope of 0. We can clearly see that it's non-zero. One thing to note is that if we change the unit of one of the two variables, like instead of measuring temperature in Fahrenheit, we can also measure temperature in degrees of Celsius, the coefficient from this linear regression will give you also a different value. In that case, a much larger value to the previous slope. You can see here, if we use the same scale in x direction, that the slope will be steeper compared to the previous one. So this means that in the end, if we are looking for a measure for linear dependency, the slope itself doesn't really tell us much about, because we can change the unit of one of the two variables, giving us different slopes. However, the underlying relationship doesn't really change. So in that example, we wouldn't expect different values. So this is why looking at the slope itself is problematic. We need some point of reference to be able to scale this value so that different units or changing the unit won't change the value itself. And for this, the so-called R-squared measure looks at the following two components. First of all, it computes the sum of squared errors of the linear line that is fitted through these points, and it compares it, here for example, takes it in relation with the sum of squared errors of a constant model that is fitted in here. And if this value here is 1, so this is a bug, this should be 0. If this value is 1, then we have the worst possible measure of dependence, meaning that the linear line or the sum of squared errors of the linear model are very close to the sum of squared errors of the constant model, meaning that there doesn't seem to be a linear dependency between these two random variables. Before we discuss the other topics, we will introduce a short recap of joint, marginal, and conditional distribution. The joint distribution is, for example, for two binary random variables computed by the relative frequencies of these two random variables. And you can see this from the values over here. The marginal distribution just sums up each value from the joint distribution with respect to one variable. For example, if we are interested in the marginal distribution of feature 1, we are summing over each possible value given by feature 2, by the other feature in the end. So in this example, we would use the sum of 0.2 and 0.3. And we do this for each possible value of the x1 variable and have the values of the marginal distribution of x1. In a continuous case, we would use, instead of the sums, the integral, which is the equivalent counterpart. For conditional distribution, essentially, we are rescaling the values of the joint distribution by the marginal distribution we are conditioning. In this example, we are conditioning on the second random variable, meaning that, for example, this value here will be scaled by this value from the second random variable here, and the value will be shown in this line over here. Dependencies tell us something about the nonlinear relationship. For example, we look at the definition of the so-called independence of two random variables. In that case, the joint distribution would be the product of two marginals, meaning that the joint distribution of xj can be written as the product of the two marginal distributions. There's an equivalent definition here based on conditional distributions, which means that the knowledge of one of the two random variables says nothing about the other random variables, meaning that if we look at the conditional distribution of xj given xk, we will always have the marginal distribution of xj, because the knowledge of xk doesn't give you more information. There are measures that are able to measure complex dependencies. For example, the Spearman correlation, which you might have already heard, is related to the Pearson correlation, but doesn't use the raw data values. It uses the ranks and is therefore able to measure at least monotonic dependencies and not only linear dependencies. Then there are also information theoretical measures like the mutual information or kernel-based methods like the Hilbert-Schmidt independence criterion. There are many measures out there that are able to measure dependencies that go beyond linear dependencies. One side note here, if two random variables are independent, the Pearson correlation will always be 0. However, the other way around, if the correlation is 0, it doesn't have to mean that two random variables are independent, because if, for example, we have a structure that looks like this, data points that look like this can result in row of x1 and x2 of 0, but we can see that there's a clear dependence structure of x1 and x2 here. Now we will look at the mutual information. Essentially, we are looking at the expectation with respect to the joint distribution of the logarithm of the joint distribution divided by the product of the two marginal distributions. And it measures the amount of dependence, so to say, by looking at how different the joint distribution is from pure independence. The easiest way to see this is by looking at what happens if we plug in the definition of independence over here, which basically ends up in the logarithm of 1 and in the end is 0. So if two features are independent, we will always get a mutual information of 0. Unlike the Pearson correlation, the mutual information is not limited to continuous variables and is also applicable to categorical. Let's make a just simple example. In that case, the expectation can be written as a sum over the two random variables that we are looking at. In that case, we have called them x1 and y. And computing this term here can be obtained from the joint distribution, which is nothing else than a table. This is an example where we have all possible combinations. In the end, each possible combination of these two binary random variables occurs with a probability of 25%. And in the end, we can use the formula over here and plug each possible value in here, and doing this for all values ends up in a mutual information of 0. And from this table we also see that the two random variables are independent because the product of the marginal distributions for each possible combination results in the joint distribution. As an example between dependence and independence, we will look at two random variables that are independent and continuous. We will illustrate that the conditional distribution is always the same as the marginal distribution in case of independence, which was the second definition of independence that we have seen. Let's look at the joint distribution, which is here visualized as a contour plot. And if we would look at horizontal slices, basically that means that we are fixing one value of x2, we will obtain this picture here, meaning that for this horizontal line, we get this curve over here. For this horizontal line, this red line over here, we get this over here. And if we would scale these curves here so that they have an area of 1, they would have the same shape, meaning that the conditional distribution is always the same as the marginal distribution of x1. The same for the other random variable, which is not normally distributed, we get the same result over here. For the case of dependent random variables, we can see here that there seems to be a trend for increasing values of x1. It seems that we also have increasing values of x2. Essentially, if we would do the same procedure here, we can directly see that the conditional distribution do not match the marginal distribution because they are shifted. Another illustration for the Pearson correlation, if we have a multivariate or bivariate normal distribution here, then correlation of 0 always means that we have two independent random variables, and correlation of larger than 0 would suggest a positive linear trend. A correlation of a negative value would suggest a falling trend or relationship. There are cases where we clearly see visually a dependence structure, like here, but the Pearson correlation gives us a value of 0. And here as well, or close to 0. And this is again a thing to keep in mind, that the Pearson correlation is not able to measure nonlinear dependencies. And the mutual information, for example, would show us a value greater than 0, meaning that it would tell us that there's some kind of dependence here.